putting it all together, let's wrap up our idea here of phases and different vapor pressures and boiling and fusion and all of that stuff. And we're going to talk about a phase diagram. Now, a phase diagram describes all the different states and the state changes that occur at various temperatures and pressures. It is a temperature, not to scale on this diagram, but still temperature on the x-axis, pressure on the y. I want to highlight here the three main curves. This is the sublimation curve. It goes from solid to a gas. This is the fusion curve. This is solid to a liquid. And then this final one is vaporization, liquid to a gas. We have combined all three of these types of changes in this phase diagram. Now, solid, liquid, gas will always appear at those positions. Couple of things we want to talk about. The point at which all three of those lines interconnects is called the triple point. The triple point is specifically the temperature and pressure conditions in which all three states exist simultaneously. For most substances, the freezing point increases as pressure increases. This is the phase diagram of water. Notice our fusion curve goes backwards. That's weird. The fusion curve typically should not go backwards like that. What it should do is go forwards. But why water goes backwards is because, remember, ice is less dense than liquid water. And that's why we see a negative slope of the fusion curve. I'll show you a couple more phase diagrams that have positive fusion curves. That would say that the freezing point increases as the pressure increases. In reality, for water, as the pressure increases, the actual freezing point of water decreases. We actually can compress ice and make liquid, which is really weird. The other point is the critical point over here. The critical point is the farthest point on the vapor pressure curve. So where we create a supercritical fluid. Lots of fun things that we can see with those and some interesting experimentation going on to see any point of this new fluid type substance that's not really a liquid, not really a gas. It's kind of a combination of both. Showing up just how to navigate this phase diagram. This is again of water, not drawn to scale, but we can see if we wanted to start at something like 1 atm and negative 25 degrees Celsius, right? If I just kind of dot this down, 1 atm, comma, 25 degrees Celsius, and then say, what happens if I increase the temperature? Well, if I'm keeping at 1 atm and I increase the temperature, I'm flowing this way, right? And I can say at this temperature right here, I would melt. At this temperature right here, I would boil, right? If I wanted to stop and say, stop at 25 degrees Celsius, what state am I in? I'm a liquid, right? If I wanted to say 1 atm and 25 degrees Celsius, and I drop the pressure, you go straight down as if you're just changing the pressure on that curve and keeping the temperature constant, you can say, hey, I transitioned at this specific pressure to a gas. All right, and so we can look at these curves and find points along the curve to identify what type of phase change are we occurring with these changes in pressures or temperatures. Or if I give you just a point, hey, at 1 atm and 75 degrees Celsius, what temperature are you at? Well, you'd say, okay, well, Lauren, this isn't drawn to scale, but so I'll estimate 75 degrees Celsius and go all the way up to 1 atm. Hey, I'm a liquid. That's how you would read this type of diagram. I expect you to be able to label solid, liquid, gas, vaporization curve, fusion curve, and sublimation curve, and of course the triple point as well. Here's typical phase diagrams for other molecules or other compounds that do not have the weird negative fusion curve, okay? Some things to just see with these ones from your textbook is that both iodine and carbon dioxide have positive fusion curves. And what that means is that the solid is more dense than the liquid. It's not like water, all right? It doesn't form that crystalline structure in the solid. Water is special. Water at a liquid at room temp is a liquid at room temperature, and most molecular substances with similar molar masses are gases at room temperature. It's probably because of the hydrogen bonding, right? Water is an excellent solvent. It can dissolve many ionic and polar molecular substances. Because of that hydrogen bonding, it is a very good intermolecular force contributor, all right? Water also has a very high specific heat, right? We've talked about its specific heat of 4.184 joules per gram degree Celsius. That's very, very high for a molecular substance. And that actually is what helps us at the coastal regions to be a little bit cooler because there's a lot more moisture in the air. And so the heat from the sun is working really, really hard to change the air temperature. But because there's a lot of moisture in the air, it requires a lot more heat energy to change per degree Celsius. So why is it cooler at the coast? Because there's more water, and therefore the ability to heat up the air and the vapor of water in the atmosphere or in the air around you takes a lot more energy. Water does expand when it freezes. That's why ice is less dense than liquid water. It's because of its structure, all right? So when we're looking at the water diagram, it will have that negative slope for the solid liquid fusion line. Everything else usually typically has a positive solid liquid fusion line.